Hello, ladies and gentlemen. Today we are going to look at an introduction to trigonometry. So for your notes today, you just need something to write with, and we're going to take down some examples and some really important information here towards the end of this video. Our key question today, and the reason for this video, is to just get an idea of what is trigonometry and what are these ratios that people talk about. And then, of course, to sort of understand where it came from. So let's first start with the understanding that right triangles are really nice. They're especially loved in the math world. They have many nice attributes. The first nice attribute is that the Pythagorean theorem can help you find missing sides. If you're given two sides of a right triangle, the Pythagorean theorem, remember, says a squared plus b squared equals c squared, and that will allow us to find a missing third side. Another nice attribute is that there are special right triangles that have cool side relationships, really neat relationships that we've been working on, like the 30-60 90-degree triangle and the 45-45 90-degree triangle. And the third nice attribute is that right triangles are similar if they have a pair of congruent non-right angles. That means if I have two right triangles, here, let me see if I can draw one here. Here's one, and here's another one. If they're two right triangles, all I would need is one pair of congruent non-right angles in order for those two triangles to be similar. Remember, similar means just one is a smaller version of the other, the same shape, but just a different size, right? And so with that idea, this is pretty much the angle-angle similarity idea, right? So as people start studying right triangles and these nice understandings about what triangles have to offer, some patterns emerge. So someone in or around India noticed that patterns happened when you have two right triangles with the same base angles, similar to the ones that I just drew. The ratio of certain sides of the triangle remain consistent with other right triangles that have that same angle. So let's consider this example. Now in this example, these two right triangles are similar. I know this because they have angle-angle similarity. Notice the 30 degrees, the 90 degrees, the 90 degrees. The right triangles are similar. So what we could do is compare one right triangle to another, like compare the 8 to the 24, the 4 to the 12, the 4 square roots of 3 to the 12 square roots of 3, making that similarity comparison, finding a scale factor. But that's not what they did. In fact, they didn't study one triangle to another. They compared the ratios of the triangle itself, one triangle, just staying on the inside of this smaller triangle here and just working with these measurements. So let's say I'm dealing with this 30-degree angle and I say, you know what, I want to make a ratio with the side opposite that 30 degrees and how it compares to the hypotenuse of this triangle. And I made that ratio, and I reduce it. And then when I go over to the other triangle, another triangle that has a 30-degree base angle here, and I do the same thing, I want to compare the side opposite it to the hypotenuse. Well, look at that. Those two ratios are the same. So we didn't compare one triangle to another. In fact, we just compared two side lengths in a smaller triangle compared to the same two side lengths in another big triangle, and we got the same ratio. It's because those base angles were the same, right? And because the triangles were similar. And we could continue to do this. Let's say we made a comparison of, let's do the adjacent side, or the side right next to the 30 degrees, or in our case, in this situation, it'd be the long leg. Let's compare that to the opposite side. And we'll do the same thing over here. Let's compare the long leg to the opposite side. And notice what happens. I reduce. I get the square root of 3. I reduce. I get the square root of 3. So it wasn't long till people discovered that that angle, that acute angle in that diagram determines the ratios of the sides of the triangle. It determines what they should work out to be. Sometimes they're not so bad, like 1/2. Sometimes they're kind of crazy, irrational numbers, like the square root of 3, like 1.71, da 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 da, you know, all the decimal values. The ratios don't always work out to be nice and pretty, but there is a consistent ratio in all triangles that have a 30-degree angle. So with that in mind, we have the development of trigonometry and what we study as trigonometry. This is a branch of mathematics that studies relationships involving sides and angles in triangles. And it is used so many places, and we're going to use it throughout the rest of this year. And there are math classes you can take beyond this that just study trigonometry. There's so much to learn. It is used to measure precise distances in math, science, technology-related fields like engineering, astronomy, architecture, aviation, military, land surveying. But it's also widely used in other fields like theater arts, digital music, music theory, and design, places you wouldn't expect it. Trigonometry deals with understanding those ratios and understanding how to set up those ratios to help us solve problems. So for our geometry knowledge, we're going to just start with three basic trig ratios for right now. They are the sine, the cosine, and the tangent ratios. And they are named that because their sides that they compare are different in each situation. So the sine ratio compares different sides of the triangle than the cosine ratio, and so on. But what you saw before is that understanding that it was that base angle, or that angle right there, that acute angle, that determined how we set up those trig ratios, or how we compute them and how we calculate them. So let's first start with the sine. The sine of theta, this is the abbreviation, SIN. Theta stands for any angle that is an acute angle in that right triangle. So sine theta equals opposite side over the hypotenuse. So when we say we're setting up the sine ratio, that's the ratio we're setting up, the opposite over the hypotenuse. And now the cosine trig ratio, so the cosine of theta, again, theta represents an angle, it's just a Greek symbol, equals adjacent over hypotenuse. Now, adjacent is the side that's right next to the angle, okay? And then tangent is the opposite side compared to the adjacent side. So we're going to set up comparison of side lengths here, and the angle is going to be used to determine who's adjacent, who's opposite, because that's more of our frame of reference. And remember, it's about that trig ratio, that angle that means that the ratio is remaining consistent. So the value of a trig ratio depends only on the measure of the acute angle, not on the particular right triangle used to compute the value. This means it does not matter how large or how small the triangle is, or where the triangle is on Earth or in outer space, the ratio will be consistent in each triangle that has the same acute angle. So we're going to learn more about how these ratios help us solve problems in days to come. But for now, we just need to get a handle on setting them up correctly. So our last part here in our notes, or our example, is to think about how we would set the ratios up. So here is a right triangle you need to draw in your notes. The triangle has the sides of 12, 5, and 13. Now we need to understand that the sine, the cosine, the tangent ratio, after that word sine, or abbreviation to sine here, comes the angle, or the theta. So in this first example, we're saying let's think about how we would set up an appropriate ratio for the sine of angle A. That means theta, or the angle we're talking about, the reference angle here is angle A. Angle A is located up here at the top of the triangle. And if we remember, the sine setup said you're going to set up opposite over hypotenuse. Well, if this is my theta, then the side opposite would be 5, and the hypotenuse of that triangle would be 13. So the sine ratio for angle A would be 5/13. Now let's look at the cosine of angle A. The cosine of angle A means I'm still talking about angle A as my reference here, but the cosine is the adjacent side over the hypotenuse. The adjacent side is the side right next to this angle, or a side that's making this angle. Now 13 is the hypotenuse, so let's look to the other side here. The adjacent would be 12. So 12 over 13. So 12/13. Now let's look at the tangent ratio for the angle A. So if I'm doing the tangent ratio is opposite over adjacent. So I'd say I'm doing 5 over 12. Now let's switch gears a little bit. You'll notice the same sine, cosine, and tangent ratios here, but now we have angle B as our reference angle. So now we need to pretend that we're down here. So here's my angle B, and now when I set up the sine ratio, I'm going to do opposite over hypotenuse. Well, in this case, opposite angle B is 12, hypotenuse is still 13, so the sine of angle B is 12/13. The cosine of angle B would be adjacent over hypotenuse. So 5/13. And the tangent of angle B would be opposite over adjacent. So in this case, that'd be 12/5. So you can see that the way we set up the ratios, we still use the same three numbers, right? But we're setting them up based on this angle or this point of reference here that we're talking about. That's because the trig ratio depends only upon the measure of the acute angle in the triangle. So that angle is our reference point, and that ratio depends upon it, okay? So we're going to be dealing more with these setups. Thank you for listening and taking good notes today, and I will see you later.